Alright, welcome to section 1.2, linear functions and regression. I don't know about you guys, but that song right there was the song of my summer. Alright, I was cruising through Pittsburgh, driving down 28, and just jamming out to that song in my car with my shades on. Anyway, back to math. Okay, we're going to talk about linear functions, which I think we're all going to be really good with today, and regression, but I can see us needing a little bit of a review on regression, and just like the first lesson, this lesson is going to be calculator based, so hopefully get out your calculator or at least have the online one ready if you have that one downloaded. So let's just start off easy with linear functions. Review of slope-intercept form. I'm thinking most of us are experts by this by now, where we have y equals mx plus b. Okay, but let's say we want to find the equation, specifically a slope-intercept form equation, between some points. So we'll have 4 and negative 10, and maybe we'll do negative 12 and 2. So we want to find the slope-intercept form equation before these 2 points. And if you take a look at slope-intercept form, we need two crucial pieces of information. We need the slope m and the y-intercept of b. So if we want to find both of those pieces, and right now the only things we really know are these 2 points, the slope might be the easiest one to find because we can find the slope between 2 points. I think most of us already know the little formula, y2 minus y1. You're just really subtracting the y's and up top of the fraction, and then you're subtracting the x's on the bottom. Now it really doesn't matter which y value you start first with. It could be negative 10 or 2, as long as you start with the corresponding x on the bottom. So for instance, even though this is my second point, or at least it's the second point written here, maybe I want to start with negative 10. It does not matter which point or y value you pick first. So I'm going to take negative 10 and subtract 2. Now, since I started with negative 10, I need to start with 4 on the bottom. Okay, these have to match up. Notice how the little sub 2's match up here as well. So we're going to take 4 and we're going to subtract negative 12, but we've got to be careful because when we subtract a negative, that actually changes to a positive. So if we continue, we have negative 10 minus 2, which is negative 12. Over 4 plus 12, which is 16. We can simplify that. Negative 12 over 16 becomes negative 3 over 4. So there's our m value. Okay, might be useful to label there. Now we just want to find the b value. So to do this, we got to go back to our points. And whenever we know a point, we know an x and a y value. So let's use some information. If we know y equals mx plus b is our slope-intercept form, let's plug in what we know. We know a y value, maybe we'll use this negative 10, equals, we know an m value because we just found that, we can say negative 3 over 4. We know an x value because we labeled this point as x's and y's, so we'll use a 4. And we don't know the b, but that's okay because that's what we're trying to find. So we're just going to say plus b. So let's solve for b because that's the only thing we don't know. We can do negative 3/4 times 4. You can think about this as 4 over 1. And since we have a 4 in the denominator and a 4 in the numerator, those two cancel each other out. So we're just left with negative 3 over 1, which is just negative 3. So to solve for b, we can add the 3 over. So that would give us negative 7 equals b. So our overall equation, y equals m, which was negative 3 over 4, x, and if we plus b, we're adding a negative 7, which is just the same as minus 7. So there's our slope-intercept form. Maybe we want to graph it. Okay, we always start with a b value, so we'll go to negative 7 on the y-axis. 1, 2, 3, 4, 5, 6, 7, right there. Slope of negative 3 over 4. Now this might be a little tricky because we would go down 3, right 4, but notice how we're off of our graph. So instead of going down and to the right, we can go the opposite direction. We can go up and to the left. So instead of going down 3, right 4, let's go up 3. 1, 2, 3, and then left 4. 1, 2, 3, 4. So somewhere right there. Notice if we were to kind of guess, if we went down 3, right 4, we'd be somewhere over here, and our line would still continue on the correct path. Alright, so a quick review of slope-intercept form. Moving on to standard form, we might remember this as ax plus by equals c. And we'll start off maybe with an example of 2x plus 3y equals 9. Now our goal for this one is we want to try to graph it just like we did the slope-intercept form. And you are more than welcome to convert this to slope-intercept form. Maybe you want to subtract the 2x. So we have 3y equals negative 2x plus 9. You can divide 3, divide everything over there. So y equals negative 2/3 x plus 3. Okay, you're more than welcome to do that because you can easily convert between standard form and slope-intercept just like we did here. But I want to take the time and show you maybe a little quicker way where this palm is going to come in. I call this the cover-up method. So our original equation was 2x plus 3y equals 9. Now maybe, okay, using the cover-up method, let's just pretend that we got rid of, oops, want to change that for a second. Let's bring that to the front. There we go. Okay, so maybe we'll pretend for the second that we cover up the 2x. Okay, so we're imagining covering our palm, the 2x. How can we solve for y? Okay, well, we're left with 3y equals 9, just as clearly seen there. And if we divide by 3 on both sides, we get y equals 3. Okay, so on our graph, since this is a y value, let's plot 3 on the y-axis. 1, 2, 3. Okay. Now, instead of covering up the x like we originally did, let's cover up the y, and I might need to shrink it. There we go. So we have 2x equals 9. Now we can divide by 2, divide by 2. You can leave it at 9/2, but since we want to graph it, maybe a decimal might work out a little bit better. 9 divided by 2 is 4.5, so maybe 4.5. Now this time, since we're talking about an x value, let's plot that point on the x-axis. This would be our x-intercept. So 4.5, 1, 2, 3, 4, maybe somewhere right there. Okay. Now since we have 2 points, you only really need 2 points to draw a line. We can connect those just like that. Now that's why I kind of call it the cover-up method, because you can use your palm to cover up either variable that you want to kind of isolate for a second. Now just to check, okay, if you did want to change it into standard or slope-intercept form, notice how you can plot the b, which is 3, just like this point was that we found before. And if we use the slope down to right 3, down 2, 1, 2, right 3, 1, 2, 3, notice how that point would be on the exact same line as we drew. So we're not necessarily going to cover up the same x-intercept like we did over here, but notice how the slope would give us another point on the same line that we found. So either way, either converting it or using this little cover-up method would generate or give you the line for this specific standard form equation. So last but not least, we have point-slope form, which has a little formula for us to kind of remember. We have y minus y1 equals m times x minus x1. And just for easiness, we're going to use the same 2 points as we did in our slope-intercept form example. Okay? And we already found the slope between these 2 points to be -3/4, right? So we can easily substitute that in for m. Now here's the thing, okay? If we're dealing with point-slope form, you need to know a point and you need to know a slope. Okay, mathematicians, I'm going to tell you guys all year, they're not very creative. When they name something, you kind of got to take it at face value. So if they name it point-slope form, you need to know a point and you need to know a slope. Thankfully, in this case, we have 2 points, okay, not just one, and you are easily able to find the slope just like we did before. So here's the thing, okay, maybe some of us want to choose this first point. Okay, so in this case, this would be our x1 and y1. So in this little formula, we have y minus, okay, this y never changes, and this x never changes, just like we have a y and an x in the slope-intercept form. So we're going to take a y and subtract the y value from our point, but if we're subtracting -10, that changes to a plus, because we're subtracting a negative. Next, we can plug in our m value. We found that to be -3/4. And then we want to take x and subtract our x value, which is just 4. right? So there's our point slope form if you choose the first point. Now some of us might be a little devil's advocate if you want to and choose the second point. You can still label this x1 and y1. So we're going to take y minus y1 equals our slope times x minus x1, but there's that negative again, so it needs to change to a plus. So depending on which point you pick, you can have either one of these two equations. Now, here's the reason why it does not matter which one you pick. Let's pretend, or just investigate for a second, changing these into slope-intercept form. So that means making it look like y equals mx plus b. So to do that, notice how this doesn't have any parentheses. Let's get rid of these parentheses. So that involves distributing our slope. So if we do that, we get negative 3/4 x. Negative 3/4 times negative 4. Negative times a negative changes to a positive. Again, you can think about this as 4 over 1. And since we're multiplying, these 4's are going to cancel out because 1's on the bottom and 1's up top. So all we're really left with is the 3. Now over here, same deal, distributing the slope. Negative times a positive is a negative. Think about this as 12 over 1. Notice how I have a 4 on the bottom and a 12 up top. We can simplify those. 12 divided by 4 is the same as 3 over 1. So all we're really left with is a 3 and a 3 up top, and since we're multiplying, 3 times 3 gives us a 9. We are left with 1's on the bottom, but 9 over 1 is just 9. Okay, so next step over here, we can subtract 10. So y equals negative 3/4 x. 3 minus 10 is negative 7. So there's our slope-intercept form there. Over here, we can add 2 to both sides. So we get negative 3 over 4x. Negative 9 plus 2 is negative 7. So we get the same exact answer. If we were to graph these two, it would give us the same exact line. So it does not matter which point you pick, because really, even though these equations look different, they are essentially the same thing. So don't be afraid about choosing the wrong point. Okay, you can't go wrong. Okay, so now that we talked about linear or line graphs for a little bit, let's talk about or review parallel and perpendicular lines. Remember, parallel lines, they never ever touch, they never ever intersect, but in terms of a graph or an equation, they have the same slope. They are increasing or decreasing at the same rate, so they have the same slope. Perpendicular lines, on the other case, they do intersect, and more specifically, they intersect at a right angle, okay, 90 degrees. Now, in terms of the slope, perpendicular lines have opposite reciprocal, hopefully I spell this right, reciprocal slopes, okay? Now, in this particular problem, we want to write the equation of a line. So notice how it doesn't say or specify what kind of equation. It doesn't say slope-intercept or standard or point slope. It just says write an equation. So you can pick any of those three that you'd like. And we're specifically wanting a perpendicular line to this line that contains this specific point. Now, that is a lot of information to kind of gather all at once. So let's just kind of break this apart. Since we want perpendicular, we're focusing on this idea right here, okay, opposite reciprocal slope. If we take a look at our equation here, we have y equals mx plus b, which is slope-intercept. So if we are specifically looking for a slope, maybe let's take a look at the slope in here. So the slope we have right now is negative 2 over 3. But in the perpendicular line, we want to make sure we have the opposite reciprocal. So we want to figure out what is the opposite reciprocal slope of this one. So we'll take baby steps. Let's find the opposite first. The opposite of negative 2 over 3 would be positive 2 over 3. But now that we found the reciprocal, or sorry, now that we found the opposite, let's go ahead and find the reciprocal. Now reciprocal just means to flip the two numbers. So we would have 3 over 2. So the slope we want to make sure we focus on is now 3 over 2 instead of negative 2 over 3. So here's what we know. We know the slope that we want to focus on, and we know the point that this line needs to go through. So if we know a slope and a point, or in other words, a point and a slope, maybe we want to use point-slope form. So that was y minus y1 equals m times x minus x1. So if we just plug in the correct information, you can label this x1, y1. We have y minus 5 equals, okay, because the 5 came from our y1. The slope that we need is 3 over 2. And we have x minus x1, but that was 4 up here. Alright, so there's the equation of the line. You can leave it like that if you want to change it to slope-intercept form. Okay, be my guest. But hopefully we are pretty familiar with the parallel and perpendicular relationships between the slopes. Alright, so now let's move on to regression. This is the point in time where you might need a calculator, so try to get one handy if you can. Regression is the process or the question of asking, is there a relationship? So is there a relationship between two things? So does one thing affect another? So is there, in this case, a relationship between the total fat in any of these sandwiches and the total calories that it would give us? So is there a relationship? You're trying to find, is there a connection between these two things? Now, in order to answer that, okay, we're going to answer some questions down here, like predicting some information. This is when a calculator is going to come into play, because remember, a calculator is a very, very useful tool. What we want to do is enter in this data, enter in these numbers into our calculator, and to do that we're going to press some very specific buttons. So maybe on the left hand side of your note guide where you have that little margin, you might want to write down the buttons we actually press. The first one we want to do is hit stat, okay, because we're essentially looking at statistics here. We're looking at some data, and we're going to hit enter so that we select this first edit option, because we're going to change something. We're going to enter in some data. Now you should have some lists, okay, or either L1, L2, L3. L1 is normally our X column, just like a table of values. So we'll assume that this is our X value and this is our Y value, just how it's written in this table. So let's just type in 9 and then 13 and continue all the way down our list. It might get a little brutal sometimes having all these numbers, but you're going to see how fast and quick this calculator is going to be able to help us out. Hopefully I'm not missing in here because I don't want to screw up. Okay, so now all of our x's are entered in. Let's scroll over to L2 and we're going to type in these calories. $60, $550, $590, $100, almost done. Is it summer yet? Okay, there we go. So we have our data typed in. Now, since we're done, we're going to hit this little quit button, but since it's in blue, we need to hit the blue second first. So we're going to hit the blue second button and then quit. So everything's entered in there. Now, what we want to do is go back to stat. Okay, now instead of hitting enter like we did before, we're going to scroll over to calc, because we're going to calculate something. Now, for this particular problem, I'm going to tell you which option to hit, but from now on, you might have to be the judge on which one you actually select. We're going to assume, since we've been talking about linear or line equations, that this data follows a linear pattern. So we're going to scroll down to option number 4. Notice how it says lin reg. That is signifying linear regression, so a line graph. So we're going to hit enter. You're going to be prompted with this page here. It's just asking you, do you want your x values to be L1, which is what we listed these numbers in, so we'll just hit enter. Do you want your y values to be in L2, which is where we put those, so we'll hit enter. And just keep hitting enter until you get to calculate and hit enter. So this little page is going to come up here, and notice how it kind of looks like y equals mx plus b, but instead of an m, they just use an a. Okay, your calculator just goes in alphabetical order. So what this equation does is it's giving us a model or an equation that shows the path or the connectedness between this information. So this is kind of useful to write down. I wonder if I can take a picture of this. We'll do screen clipping. There we go. Okay, so here's a little screen clip. we'll do y equals a, but our a value we'll say is 11.73. We have our variable x, and we want to add the b value, which was 193, we'll say 0.85. Okay, so here's the linear equation. It's a slope-intercept form equation that predicts or shows the path of this data. So what we want to do is predict the calories of the grilled cheeseburger that has 79 grams of fat. So if this is 79 grams of fat, notice how we said that was an x value. If we put 79 in for x, let's see what we get. So let's clear that out. We're going to predict some data. 11.73 times 79 plus 193.85. Alright, so we have 1120.52. So we can say 1,120 point, what was it? 52? 52 calories. That's a lot of calories. So this grilled cheeseburger, 79 grams of fat. Notice how that's a big number off of our data. Okay, so we're going to use this equation to predict. Since this number is not included in our data, we can actually predict or guess what it would actually be. So we can use that equation to help us out. Assuming that there's a correlation or a connection between this information, we can predict data. Now, on the other hand, let's predict fat grams if we know a calorie. So since 800 is a calorie, notice how that's a y value, we can put 800 in there. So we have 800 equals 11.73x plus 193.85. So this time we want to solve for x. That's our fat grams. So if we subtract 193.85, move this over here, we're going to take 800, subtract 193.85, so 606.15 equals 11.73x, and our last step is to, I don't want that one, just divide by 11.73, and we get 51.68, we'll say. Okay, so x equals 51.68 fat grams. There we go, fat grams. So again, notice how 800 calories is kind of off our list here. We're going to use this equation to predict information. Alright, so before we go on, I want to show you one more thing about this calculator and this regression that is going to be very, very useful. Your data, if we go back to stat and enter, is already programmed in here. Okay, so you have this data in your calculator, and if you hit graph, notice how you can't really see anything, but what we can do is this stat plot option right here above the y equals, we can turn this on to show a scatter plot, okay, little dots on a graph. Now notice how our plot 1 is off. If we select that, it's programmed as off. We can select on, turn it on, and this first little option here is just going to plot some dots. So that's what we want to make sure is programmed, and we have L1 and L2 that all of our data is programmed in, and these dots that we plot are going to look like little squares. You can change them to plus signs or I guess little circles, but they're going to look like little squares. So if we turn that on, we can't really see anything just yet, but that's because we need to change our window. So let's use the data to help change our window. The x min, okay, the lowest x value I see is 5. So maybe we'll just go a little bit lower than that. We'll say 3, just so we see it all. And the highest x value we have looks like 34. So maybe I'll go a little bit higher, make sure I can see it. We get 36. And maybe I'll count by 3s instead of 1s. For the y values, these are a little bit bigger, but the lowest one I see looks like 260. So maybe I'll go a little bit lower. We'll say 250. And then the highest one, we have 590. So maybe we'll go a little bit higher, just 600. And this time maybe we'll count by 50s. So now we should see something when we hit graph. And look at your data, okay? All of these different little squares right here are these data points that are stored in your calculator. So this is an actual scatter plot of this information, and notice how the path really looks like a line. Okay, it's really linear, which makes sense because that's the type of equation we found. And if you actually want to type in the equation, we can do 11.73x plus 193.85. We can see how close this line actually is at predicting. And notice how it's actually really good, okay? It goes through the middle of almost all of our data points. Now, this one, notice how it's kind of cleared, or not cleared, but filled in. That means that the line is actually going through that data point. So whatever data point that was on here, it actually fits this equation. So this line right here is called the line of best fit. It's the best line that's going to predict information for you. The line isn't going to be able to go through all the data points because after all, then it wouldn't be a line, it'd be a lot more jagged. But this is the best line or equation you can use to predict data. So I think using a scatter plot and actually visualizing what this information looks like on a graph can be really useful. We're going to do this again in another example in a little bit, but I figured I'd touch on it right now. Alright, so just a quick review of graphs. I'm going to add one on your left-hand side. You might want to add this in here. It's just a linear graph that we talked about before. And we're going to take a look at two different types of not different types really, but different shapes of graphs if we have a positive graph or a linear graph. Now when it comes to regression, okay, if you remember, if I bring up the calculator again, if we hit Stat and over to Calc, okay, we had a lot of different options here. We used the linear regression in our first example, but we could have quad reg, okay, which is just an example of quadratic regression. We could take a look at cubic regression. We could have quartic, probably not, but you could. We could talk about exponential regression, which is right here. And I think we have a square root one. Maybe. I actually think it's under power regression. And there, okay, power regression, if you want to write that down, means kind of the same thing as square root. But depending on what your scatter plot looks like, we're going to go over these graphs again to kind of help you out. You can determine which regression actually fits your data best. So for linear, we know a positive linear graph goes upwards to the right, whereas a negative one goes downward when you're traveling from left to right. Quadratic, hopefully we remember this from Algebra 2. A positive quadratic graph looks like a U shape. Okay, it's called a parabola. Whereas if it's a negative one, it's actually going upside down, like an umbrella. Square root, we have this starting point and it kind of gradually goes up and to the right, whereas the negative gradually goes down and to the right. Cubic, we have this funny looking curve. I don't know how best describe it. And if it's negative, it kind of flip-flops. So instead of going down, up, this one goes up, down when you're talking about left and right. Exponential, you gradually start and then you kind of shoot upwards, whereas the negative one shoots downwards and then gradually goes right. Okay, so hopefully you kind of remember these from Algebra 2. Maybe they're a little stuck in your memory. Maybe you haven't seen any of them before. Don't worry about it. We're going to go over these eventually later this year. But these are just some quick notes, quick reminders about what these different types of graphs look like. Alright, so last but not least, we have our final example here. Maybe you want to pause the video and try this one on your own, but if you're not feeling quite comfortable with it just yet, you can follow along as I go through it right now. So we have the table below, and it lists the number of Americans in thousands, so this is 50,000, 56,000, who are expected to be over 100 years old for the selected years. So in 1994, there were 50,000 Americans over the age of 100. So what we want to do is enter this into our calculator and find a friendly window so that we can see the scatter plot. So let's bring up our calculator again. Okay, we want to go to the Stat button and Edit. Now we should have the data in there from the last example. Now to clear it out, we want to scroll to the top, select L2 and hit Clear. And then just arrow back down and it should get rid of everything, and we can do the same thing for L1. Now here's the thing. Typing in 1994, 1996, and so on are really, really big numbers for your calculator. because your calculator doesn't know the idea of dates, okay? It just knows strictly digits or numbers. So to make it easier for our calculator, instead of using 1994, we're going to use 0, because that's kind of our starting year, and then we'll use 2, 4, 6, 8, and 10, just to show the progression of 2 years in each step. So make it a little bit easier for our calculator. 2, 4, 6, 8, and 10. Now, these we can type in no problem, because those are fairly easy. Notice how the table already made it easy for us. Instead of listing 50,000, 56,000, it kind of truncated it. It just shortened it for us, and we're talking about a smaller digit. But it's really important that when you go back into the problem, you really are careful about your numbers. So if we get an answer of, I don't know, 90, it's not representing 90 people, it's 90,000 people. So we really got to be careful with the units that our table gives us. Alright, so there's our information. The first thing we want to do is find a friendly window. So let's go to our window. And our x's are going from 0 to 10, so let's change that. And maybe we'll count by ones. Our y values are going from 50 to 110. Maybe I'll go a little bit lower than 50 and a little bit higher than 110. And let's say we count by tens. Okay, let's hit graph. So there's our data. Okay, there's our data points. And the reason we can see this now is because if we go back to stat plot, okay, our stat plot is on. But notice how maybe you didn't want to see the data points. You can just select the off option and you will no longer see them. Okay, so since we're specifically talking about our scatter plot, we really want to make sure that we can see those points, and our scatter plot has to be on. Now, there's our window. So maybe we'll write down those values. Let's see, we had 0 to 10 and 1, and then 400 to 100, or 40 to 120 and 10. So we had 0, 10, 1, 40, 120, and 10. So there's our window. Next, we want to determine the function that best represents the data. So taking a look at our scatter plot, what kind of graph does it look like? Okay, so these are our quick graphs. We want to see what shape does it resemble. Does it look like a line? Does it look like a parabola? And if you kind of imagine, a line isn't really going to get close to all of these. It might get close to maybe 2 or 3 of them. But notice how the general shape is kind of curved. So maybe a curved graph might fit better. And I guess the best curved graph that could fit would probably be a quadratic, because it has this upward motion. Okay, the square root is curved, and the cubic is curved, and the exponential is kind of curved, but they're curved in different ways. So maybe we'll try the quadratic. So let's try, or write down quadratic. And it's actually, number 3 wants us to use regression to find the model, or in other words, what's the equation that would best represent this data. So let's go to Stat, over to Calc, and this time we want to select quadratic regression, which is option number 5. And it's going to ask us the same questions. Are you sure you typed in your x values in L1? Are you sure you typed in your y values in L2? I'm pretty sure we did, so let's just calculate. Alright, so we have these values. Notice how we have an x squared in there, meaning it's quadratic, and we just want to maybe round these answers and put them in A, B, and C. So we'll screenshot this. There we go. Okay, we'll put that right, and we'll put it up here. Okay. So our equation, we have A, which it tells us is 0.40, maybe 2. We have x squared. Then we need to add b, so we're going to add 2.04 x, and then we want to add c, which is 50.07. Okay, we'll just round those. So there's our model, there's our equation. Now we want to use this to predict the number of 100-year-old Americans in 2010. So this 2010 is a year, but we want to make sure we convert it to the easier or smaller numbers that we were using before. All right, so 2010 is how many years since 1994? Well, 2004 was 10 years, which means 2006 is 12, 2008 is 14, and then 2010 would be 16. So the x value we want to specifically look at is 16, which means we can plug that in to these x's. Or, remember, you can use your calculator to help you with that. If we go into y equals and type in our equation, we have 0.402x squared plus 2.04x plus 50.07. There's our graph. And notice how close it actually is to our scatter plot. It's actually going through 1, 2, 3 of these data points. Okay, these data points are falling exactly on this curve, and the other ones are pretty darn close. So if we hit the trace button and we want to see an x value of 16, remember you can just type in, trace. Oh, I know why. See this P1, L1, L2? Okay, it's specifically tracing your data points. Maybe we'll scroll through those. Or if you arrow down, this time it's selecting the actual graph. So since we want to type in 16, we want to make sure that our actual graph is selected. So now we can hit 16. And why is it not working? Oh, I know why. Because notice how our x max only goes to 10. And since we want to select 16, we want to make sure it's included in our window. So maybe we'll go to 20. All right, so there we go. There's our data. And if we hit trace again, make sure we arrow down so our equation is up top. We can select 16, and there's our answer. So in 2010, we can have 185, we'll say 0.6 thousand people, remember this is thousands, over the age of 100, all right? So now we want to predict when will there be 80,000 100-year-olds in America. So really we want to check out and see when do we get 80 in this y answer or table. So let's scroll through, and remember we want to try to find 80 as our y value. So here we go, scrolling. Try and get as close to 80 as we can. Are we there almost? We'll say that one's close enough. All right, so 81, pretty close to 80. We'll round that to 6. All right, so our x value is 6.6. But remember, this is 6.6 years after 1994. All right, so 6.6 years after 1994 is about 2000. So we'll say in the year 2000. Now, since it's 0.6, okay, maybe this will be like September in 2000, but in the year 2000, there will be over 100-year-olds in America. All right, so hopefully we're getting a little bit better using the calculator. We're going to have a little bit more practice with this in the application and the practice set. Remember, don't be afraid to ask for help. I know the calculator can be daunting sometimes, especially when you're not familiar with it, but I promise you the more we use it, the more we're going to like it and the better we're going to get at it. So don't be afraid to ask for help. Good luck on the practice, the application, and the mastery check, and I'll see you guys next class.